Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. We have an awesome paper to talk about today. It's about analyzing anisotropy in creep of additively manufactured materials. So creep, this is when materials slowly deform over time, and this is super common in metals. But did you know that in additively manufactured components, it can creep more in one direction than the other? Like it might creep more in the build direction than transverse, or vice versa. And this team, which comes from Argonne National Laboratory led by Sagar, Bhatt, set out to investigate that and try and understand what's going on, can they model it, and what insights can we take about additive manufacturing to improve the process going forward. Okay, first off, they do point out there has been quite a bit of effort to understand this in the past. A lot of 2D approximations and these sort of 2D models, they're interesting. They can explore the role of texture, porosity, morphology, but you miss the complete picture when you only look at the 2D picture. So we're going to do better off if we can do the full three-dimensional picture, which means we're going to rely on crystal plasticity finite element models. So here's an example of a simulated microstructure on the left from some sort of structured grid. And on the right, you've got the polycrystal mesh generated from this microstructured data. So now you can actually turn loose your crystal plasticity finite element model to simulate performance on this thing. Specifically, the authors are going to try and explore the performance as a function of three parameters: the grain shape, the grain morphology, and the void growth along the grain boundaries itself. So if you look at this figure here, they're essentially showing you strain versus time. So the strain rate would be the slope here. And you've got it as a function of the build direction, whether it's the transverse, like the laser path, X or Y, or the build direction defined as Z. And what you're seeing here is that even if there's no preferred orientation, which the pole figure on the left is showing, it's not like there's any texturing here, you're still seeing higher creep in the build direction. And that kind of makes sense. If you think of the LPBF process, it's known to produce these elongated columnar grains in many cases. And if you have that, then you have a longer path where dislocations can travel without being obstructed, right? If you have fewer barriers, then you have easier deformation and therefore faster creep. That sort of makes sense. And interestingly, it didn't matter, even if you took a very simplified structure like this one where it looks like shipping containers stacked up versus a more realistic structure, you get the exact same results. So the shape alone is very important here. Another thing that I thought was interesting is when they started to explore the impact of these cavities that can exist along grain boundaries, right? Should these play a role or not? Interestingly, if you look at the grain size on this figure on the right, up until about a couple microns, it doesn't really change the creep strain rate. But after a critical size, around 2 microns in this material, you actually see that it changes and it flips it. Whereas before you saw higher strain, creep strain in the build direction, now you start to see higher creep strain rate in the transverse directions, which is a really interesting finding. The authors explain why that might be happening, essentially arguing that these grain boundaries in these directions start to see higher stresses, which can then accelerate void growth and failure. I think this is pretty slick. The observation that sometimes creep is faster in the laser path direction and sometimes it's in the build direction, now they're proposing a potential solution to explain the sort of long-standing mystery in that it depends on defect size. So if you have a totally clean material where defects aren't present, then you might expect to see higher creep in the build direction. But if you have a defect-rich material, and depending on the size of those defects, you could actually see it showing up faster in the laser path direction, the transverse direction. Same material, different microstructures, different behavior. This is great. It's going to help us understand more reliable additive manufacturing components, and I hope you'll read all about it in the latest issue of IMMI.